Welcome to today's explainer. Okay, we are going to dive right into something truly fascinating about the future of green computing. We're looking at a radically simple, everyday metaphor that's actually solving one of the absolute most complex thermodynamic bottlenecks in artificial intelligence today. We are talking about giving AI a bicycle transmission. Specifically, we'll be breaking down exactly how the brand new NVIDIA Blackwell architecture is leveraging this concept to run what's known as stochastic inference. It's an absolute game changer. But to really understand why this solution is so brilliant, we first have to talk about the fundamental flaw in how AI infrastructure works right now. Currently, our large language models are essentially brute forcing every single output token through massive, super power-hungry mathematical operations. Think about that for a second. Why on earth are we burning the exact same raw computational energy to generate a basic grammatical word like the or hello as we are to solve deep, complex logical reasoning? It just doesn't make any sense, right? It's incredibly inefficient. And this brings us to a really intuitive metaphor. When you think about riding a bicycle, you inherently know you don't try to climb a steep, grueling mountain in 10th gear, and you certainly wouldn't pedal down a flat, smooth highway in first gear, just furiously spinning your legs out for no reason at all. Yet, believe it or not, our current AI infrastructure runs every single model in a single rigid gear. It's totally locked into one power-hungry precision, entirely ignoring the terrain of the task it's actually doing. Now, you might be wondering what's actually causing this massive energy drain. Well, the root of the AI energy crisis isn't the math itself. It's a thermodynamic bottleneck called the memory wall. In autoregressive decoding, over 80% of the total GPU power is completely wasted just driving high-speed memory buses. It's literally a thermodynamic tax just for moving heavy static weight matrices from the VRAM over to the compute cores. We are wasting massive amounts of energy just shuffling data around inside the hardware. So, the big question is, how do we break through that wall? Enter SDSIE. That stands for the Software-Defined Stochastic Inference Engine. This is our bicycle transmission for AI. It acts as an automatic, multi-geared transmission sitting directly between the AI model and your hardware. And the genius of it is that instead of permanently degrading a model's intelligence with traditional static quantization, SDSIE keeps the master model completely pristine, but it dynamically shifts the AI's precision on the fly. When you put this into a complete processing pipeline, it works in 3 really elegant steps. First, you have a hyper-quantized lightweight draft model, a speculative scout, that generates quick candidate tokens. Then, an entropy router monitors the AI's confusion level to decide which gear it needs to be in. And finally, dynamic resolution kernels, using custom Triton code, execute the math at the perfect precision level. It creates this beautifully continuous, seamless flow of data. But how does the router actually know when to shift those gears? It uses something called Shannon Entropy. In information theory, this is a real-time measure of uncertainty. But for our purposes today, just think of it as the AI's internal compass for mapping out the steepness of the cognitive hill. If the AI is generating really predictable syntax, entropy is near zero. But if it hits a complex, multi-layered reasoning problem, boom, entropy spikes. So mapping this back to our bicycle gears, when the AI is confident and cruising on a flat highway, it shifts into a Sub-Byte int4 high gear. It packs the data tight, uses way less VRAM, and just flies through the generation. But the second the AI gets confused and entropy spikes, meaning it's hit a steep cognitive hill, it instantly downshifts into full FP16 or BF16 low gear, making sure to reserve full computational power for that complex reasoning. Now, if you've ever driven a car with a finicky automatic transmission, you know all about gear hunting, when the car rapidly shifts back and forth because it can't quite decide what gear it wants. To prevent this kind of pipeline thrashing in our AI, SDSIE uses a Schmitt-Trigger clutch. It's essentially a dual threshold deadband. Once the gear is engaged, it locks firmly into place until a clear, sustained shift in context absolutely demands a downshift. It perfectly ensures the AI's chain doesn't slip. Just to put this into perspective, let's look at live telemetry from a really complex poem generation, specifically a chant royale being written by Llama 3.1 8B. You can see the clutch locking into a high gear for the predictable meter of the poem, but right at step 32, during a really tricky rhyme transition, the entropy suddenly spikes to 2.98 bits. The clutch instantly drops into single-step fallback, effectively downshifting to handle that complex rhyme scheme without wasting a single computational flop. It's pretty amazing to see in action. Okay, theory is incredible to unpack, for sure. But what you should really take away from this explainer is how it actually performs in the real world. We aren't just talking about software simulations anymore. This framework has been thoroughly tested on bare metal, cutting-edge hardware. We are talking about the brand new NVIDIA RTX 590 Blackwell architecture. By tying this software transmission directly into Blackwell's tensor cores, the results are just phenomenal. When you actually run this on Blackwell silicon, the drop in energy consumption per token is dramatic. What's even more impressive is that for standard code and syntax, the Blackwell GPU spends nearly 95% of its time cruising in that highly efficient Sub-Byte int4 high gear. It really proves just how compressible AI logic actually is when you finally give it the right transmission to work with. Let's rapid-fire some of these Blackwell metrics because they are genuinely staggering. First up, a 46.7% reduction in raw energy expenditure. We are talking about dropping from 6.40 joules down to just 3.41 joules per token. That is literally almost half the power requirement, just entirely erased, simply by letting the software shift gears intelligently. Second, and perhaps the most critical metric for actually overcoming that memory wall we talked about earlier, a 71.9% reduction in memory bus traffic. The custom Triton kernel running on Blackwell radically slashes the VRAM bandwidth tax per projection layer. It's just moving significantly less data across the board, which is a huge bottleneck relieved. Third stat for you, 94.7% code compressibility. Think about what this means. When you ask an AI to write a Python script, all that routine boilerplate code, the standard syntax, the predictable doc strings, it runs almost entirely in that ultra-efficient Sub-Byte high gear. It saves all the heavy lifting purely for the actual complex logic blocks. And finally, because we are clearing up that memory bottleneck and moving data so much more efficiently, the generation speed actually jumps. On the RTX 5090, throughput velocity increases by 47.3%, hitting a really impressive 34.91 tokens per second. We are saving massive amounts of energy while going significantly faster. It's a total win-win. So why does all of this matter at scale? Well, let's translate these micro-level hardware specs into macro thermodynamic benefits. If you apply this SDIC transmission to a medium-sized enterprise cluster of, say, 512 GPUs over a single year, the math is just undeniable. You're looking at over $218,000 in operational expenditure savings on electricity alone, and the avoidance of 474 metric tons of CO2 emissions. It is a massive, massive leap forward for green computing. Section 1, the physical horizon, beyond software. While SDSIE is an absolutely incredible software workaround for today's rigid hardware, the true horizon is physical. Tomorrow's non-von Neumann hardware will run these stochastic gears natively. We're talking about probabilistic bits that fluctuate to execute complex Bayesian inference asynchronously. Or analog in-memory computing, which completely eliminates those power-hungry converters. Or even ionotronic MEM transistors, using 2D materials to create synaptic pathways directly in the circuitry. The hardware itself is literally becoming stochastic. Which leaves us with this final thought. We know that AI models are only going to continue to grow in scale and complexity, right? The brute force era of static compute is rapidly reaching its thermodynamic limits. So the real question is, will our future hardware adapt to think less like rigid, power-hungry machines and more like a fluid, intuitive bicycle ride? Well, if the stochastic inference results on Blackwell are any indication at all, that shift is already well underway. Thanks so much for joining me on this explainer, and keep your gears turning.